Okay, here's the second video on Chapter 9. I'm going to introduce I'll talk about ionic bonding, and if time permits, I'll talk about metallic bonding as well in this video. As you remember, in the first one, I introduced the three main types of bonding: ionic, covalent, and metallic. So let's first take ionic bonding. So in ionic bonding, it's a bonding between a cation and an anion. Typically, a metal that's given up an electron to become a cation, and typically a non-metal that picks up an electron and then becomes an anion. These ions will arrange themselves in a solid lattice, kind of interchanging plus and minus. And I'll try to draw a picture of this in a bit. So, again, the main characteristic of this form of bonding, when kind of focusing on the electrons, is that in this case the electrons are actually truly transferred from one atom to the other, and actually it goes from the metal, which is has a less electron affinity, to the non-metal, which has a higher electron affinity. So let's take an example. Let's take an example of sodium chloride. Okay, so sodium chloride. Let me first kind of draw the Lewis dot notation. Sodium has the configuration of neon, but it has one valence electron that's in the 3s orbital. Chlorine also has the configuration of neon, but it has 2 electrons in the 3s orbital, and it actually has 5 electrons in the 3p orbital. Okay, so chlorine has a total of 7 valence electrons, where sodium has just 1. So that's the orbital notation. I'll draw the Lewis dot notation. Sodium with its 1 valence electron will look like this. Chlorine with its 7 valence electrons will look like this. Okay? And when they combine and form an ionic bond, what happens is that this electron is the guy that moves over to this little vacated spot here. And what you end up with from the dot notation is you have sodium with no electrons, so it has a plus charge. And you have chlorine now with 8 electrons in its valence shell. And since it has 1 more than it's supposed to, it has a minus charge. Okay. So try to draw this as best I can in a lattice, in a solid lattice. These ions, again, they attract each other because they're of opposite charge. And what you'll see is it'll look something along the lines of, and I'm not going to use the symbol, I'm going to use a plus and a minus, but you'll have a plus and a minus and a plus and a minus and a plus and a minus. And again, these are just depictions of either the cation or the anion. And this lattice will proceed in 3 dimensions. So if I could possibly draw that, you'd see it kind of looking like this in the other direction, and it forms a nice, very stable lattice. When I mean by stable, I mean actually a low energy state, meaning it would take quite a bit of energy. In fact, it does take quite a bit of energy to disrupt this lattice. And we'll talk about what this means for some of the physical properties of ionic compounds. Okay, we'll do that in a second. Now, what is it that I want to say about this next? Oh, yeah, I know what I want to say. So I introduced, I just said a concept, which is a lattice energy, basically the energy of the lattice. The lattice is stable and has a nice arrangement of fairly close arrangement of positive and negative particles, and therefore it is a low energy state. I want to talk about that energy, or the energy essentially contained in that lattice is known as the lattice energy, or it's also sometimes depicted as the delta H lattice. Okay. Now, there's an interesting thing about this, and I've actually mentioned in several videos, you've heard me say that sodium likes to give up an electron and chlorine likes to accept an electron. And when I say, I always kind of qualify that by saying, what I mean by likes is that it obtains a more stable state from an energy standpoint, and that's why sodium likes to give up an electron. Well, that isn't actually even totally, completely accurate. And I want to kind of talk about that a bit. Is that when you take sodium, a sodium atom, and you pop off one of its electrons, resulting in this situation where a sodium cation and an electron. This actually requires energy. So when I say likes, that's a bit misleading. But you'll see kind of why I say that in a second. But conversely, if you have a chlorine atom and it picks up an electron, forming a chloride ion, this actually releases quite a bit of energy. So because chlorine is, well, chlorine is very electronegative, it has quite an electron affinity, and when I say it likes to grab an electron, the delta H of this step is quite negative, and the delta H in this step is a little positive. Okay. Now, that still doesn't explain why by the sodium chloride ionic compound is so stable. And the reason why it's so stable is really neither of these steps. It's stable because of what's known as the lattice energy. So I'm going to kind of draw, and there's an example in the book that talks about this, and it's something called the Born-Haber cycle. And I'm going to take this exact example we've been talking about, even though the book talks about a different or similar reaction. But if we look at, I'm going to draw a state here. If we look at a reaction of taking sodium metal and reacting it with, I should actually, hang on a second. I'm going to switch pens because this pen isn't as good. If we take sodium metal and react it with chlorine gas, this forms sodium chloride as a solid. And this reaction that I drew is actually very exothermic. It releases quite a bit of energy, total. But the lattice energy, it turns out, ends up being the predominant reason why this reaction is exothermic. So I'm going to take you through the cycle. So the cycle kind of goes like this: is that when you take a look at this reaction, you can see it. You can actually envision this as requiring a number of steps. Okay. So the first step. So this is actually kind of at a certain level is where this is now enthalpy here, energy on the left. And so these reactants start at a certain energy level, like right about here. Okay. So the first step can be seen as taking the sodium as a solid and turning it into a sodium atom as a gas. Okay. And so this arrow that I drew, the vertical arrow, requires energy to essentially take a solid sodium atom, which is in a metallic lattice. I haven't talked about metallic bonding yet, but the sodium atoms are all bonded together in a metallic lattice, and it requires energy to pull off an atom from that lattice and turn it into a gaseous atom. Okay, so that requires energy. That's positive energy that we have to put into the system to make this happen. Okay, we also then have to go even a bit further to deal with this chlorine molecule, which is bonded together. So when we go to this next level here, we're going to have a sodium atom, it's in a gaseous state, and a chlorine atom, also in a gaseous state. So here we took essentially half of a chlorine molecule, which is two chlorine atoms bonded together covalently, which we'll come to in the next section. And we had to split that apart. So there's actually energy in that bond that we have to break. So this arrow going up here is more energy that we have to put in the system to break the bond, the chlorine molecule bond. Okay, and then we get to this step. All right, there's another one here, which is, these are all steps that we have to add energy to the system. Is that now the sodium atom in gaseous form turns into a sodium ion, and an electron and a chlorine atom. Okay, so again, this arrow reflects the fact that it requires energy to pull off an electron from, that's basically the ionization energy of sodium. It requires to actually add energy to the system, pull an electron off of sodium. Right, now we finally start to get some of this energy back. The next step in the cycle is to drop down to where we actually have a sodium ion, and now the electron joins up with the chlorine atom to form a chloride ion. They're both still in the gaseous state. Okay, and so here now this represents the electron. This is a negative step because the chlorine atom has quite an electronegativity, an affinity for this stray electron, and this process actually releases energy back. So first one of our steps that actually releases energy. But see, now that we have a gaseous sodium cation and a gaseous chloride anion, finally the last step takes us down here, where you finally have sodium chloride as a solid in a lattice. Okay, this step is huge, and this step here is known as the lattice energy of sodium chloride. And so if you remember Hess's law back when we talked about this in chapter 6, I believe it was, you can add up all of these states, these enthalpies, and even though the reaction it probably doesn't involve all of these steps as individual steps, still we can actually, if we can measure these steps in other ways, we can add them all together to essentially calculate whichever energy we don't know. And this is actually a common way of actually calculating a lattice energy, because it's easy to do this overall reaction and measure the overall delta H of reaction, which again is exothermic in this case. So you could do this reaction in a device to measure the enthalpy change of the overall reaction, measure this, and then given that you can find the rest of these that have already been predetermined, we can then calculate what the missing energy drop here is for the last energy. Okay. Now, a couple of things I want to also say about ionic compounds in general, and again, if you remember back, I wish I hadn't erased my my little nifty lattice picture. I'll draw it back here just for a second. I'll only draw it in 2 dimensions, but again, it is 3-dimensional. Is that the electrical arrangement here actually shows or actually explains why some of the properties of ionic compounds are the way they are. For example, they're very rigid and brittle. You can't actually pound them into shape. They're not malleable. And in fact, if you were to actually strike one side of a lattice, it doesn't want to move. But if you struck it hard enough, what would happen here is that, let's say I had a big hammer and I struck it right here. This plus and minus plus would tend to shift down like this. And you'd see now we'd have a situation where the instead of them being a positive next to a negative, you got a positive next to a positive and negative next to a negative. This whole process would continue down the dimension here that we struck it in. And once we struck it hard enough, the thing would just be brittle. It would crack. It would crack along this line because of the electrostatic forces now introduced in between the lattice. You'll see that this is not the case in metals. And I'll talk about that next. There are other factors here, and maybe I'll touch on them when I start the next video and talking about metals. So I'll end this now. I'll pick back on a few more comments by ionic compounds and then talk about metallic bonding.